Hi everyone, I'm Chen. This is joint work with Professor Ivor and Professor Associates, and the title of our paper is Unlearning Misalignment for Personalized LLM Adaptation for Instance Response Dependent Discrepancy. Large language models, or LLMs, are now everywhere, powering everything from chatbots to productivity tools. But here's the thing. While they are good at generating text, they are not very good at generating text the way you want it. And that gap, personalization, is what this talk is about. Think about models today are trained on broad general purpose dataset. The job is to predict next words, not to adapt to your slang, your tone, or your cultural style. If I say kopi O in Singapore, that means black coffee with sugar, but to the model it might just look like a random tokens or mistranslations. Same with sables, blend shifting, or let's makan, let's eat. These are natural to local, but the model misses them. So it's not just about the slang. If you are a small business using API-based LM, the model doesn't remember your preferences across sessions. You correct it once and it forgets the next time. So the real challenge is, how do we make LM remember and respect user preferences consistently without costly fine-tuning or hidden proprietary memory? Overall, the goal of this work is quite straightforward. We want to equip large language models with the ability to remember and consistently follow each user's preferences so the response stay aligned over time. But to get there, we first need to overcome two big obstacles. The first is preference recognition. Current models often fail to notice when the output drift away from users' latent preferences. In other words, they don't always recognize misalignment when it happens. The second is preference retention. Even if model does get correct once, it usually forgets that correction in later interaction. The learning doesn't carry over. So personalization isn't just about spotting the differences, it is also about holding on to it session after session. Let me walk you through these figures to clarify the differences between prompting and all methods. On the left, in the panel A, we see the standard prompt-based setup. Given an input called it X, the assumption is that we can always reach the user preferred response by finding the right prompt strategy Z star. This is essentially what prompting does. It maximizes likelihood by searching for the prompt. But in practice, even with the so-called optimal prompt, the LLM's output, let's say it Y prime, often deviates from actual user preferences Y. Now, in panel B, we see one kind of deviation we call instant dependent discrepancy. Here, the output Y prime deviates from Y regardless of the input. Think of this as random noise. The model just sometimes fails even when the input is the same. But more importantly, in panel C, we see instance response dependent discrepancy. In this case, the mismatch between the Y prime and the Y depend on the specific input X. This is a more realistic case. For example, if query includes copy all or can or not, the model systematically misinterprets, so the error isn't random, it's tied to the input itself. And this is exactly the gap existing prompting methods overlooked. Prompting assumes that with the right Z, the model will always generate the correct Y, but in reality, deviations do happen and they are often input dependent. Let's look at the likelihood view of prompting. Given equation 1, what this means is that prompt-based learning tries to maximize the likelihood of generating the correct output by searching for the right prompt Z. The assumption is simple. If we find the right Z, then the model distribution will produce the desired response. But here's a limitation. This works if the input X is well represented in the training distribution. If X is out of distribution, say it contains cultural slang or user-specific phrasing, then the model has no guarantee of generating a correct or aligned response, no matter how many prompts we try. So maximizing likelihood through prompt engineering improves correctnesses only when the simple distribution match training data. It does nothing to address systematic misalignment in subjective or unseen input. This brings us to our key idea: model the discrepancy. Here, y prime is the observed LM output and y is the latent user preferred response. The critical Newton P y prime given y and x the instance response dependent discrepancy. This term captures how models' output diverge from user expectations given the input. Now let's talk about implementation. The process is simple and lightweight. First, we collect a small set of user preferences pair, for example, input with a slant and a corresponding verified output. Second, we estimate discrepancy between the models produced and what user actually intend. Third, we store this discrepancy in a lightweight memory bank. Finally, when a similar input shows up again, we record the discrepancy and correct the response by marginalizing what we have already stored. So the intuition is straightforward: collect, estimate, recall, correct. Instead of assuming LM is always right, we actually learn from its mistakes and use those every mistakes to align future response. Now let's compare our methods consistent marginalization against popular prompt-based methods. Few short prompt is good for general task performances, but it cannot adapt to user-specific feedback. Chain of thought improves reasoning, but it is prone to hallucinations and it ignores personalization. Self-consistency uses majority voting, which can help accuracy, but it does not help to align with the user. Self-refined integers iterative self-correction, but it is computationally costly and again it lacks memory. By contrast, all methods consistent marginalization explicitly models discrepancy between LM output and user preferences. It delivers strong personalization alignment. Remember, paths are misalignment and requires node per user fine-tuning. So the big picture in these prompt-based methods are primarily correctness enhancer. Consistent marginalization, on the other hand, is a true personalization enabler. We evaluate CM on ChatGPT 4o mini, ChatGPT 3.5, and the Lemma 8 billion instruct across 5 datasets. Using only 5% user preference samples, CM consistently improve alignment. On banking with ChatGPT 3.5, performance jumped from 19 and 6% with chain of thought to 9.0% with chain of thought plus the COT, again of over 12 points. We also saw a strong cross-lingual gains on MOTE and MS. Improvements were robust across backbones, though less pronounced than the model trained directly on their own discrepancy. So CM works with minimal data, scale across language, and generalize across model families. These tables show that CM is effective even with limited user preference samples. With just 5% of user preference samples, CM boosts every baseline on Lemma 8 with large jump on banking. COT plus CM improved by 12.7%. Most other datasets see solo gains of 3 to 8%. Even at just 1% user preference sample, CM still showed robust performance gains. CM remains effective in ultra-low label regimes, showing you don't need much annotated data to get meaningful personalization. Large language models are powerful. They master facts, they generalize, but they do not see you. They ignore your preferences, your style, your history. Consistent marginalization changes that. It remembers your preferences, learns from very little data, scale across platforms and deployments, transform static agents into ones that adapt to you. We have built machines that knows everything. Now let's build machines that know you. Thank you for your time.